Hello, AB Physics 1 students. Make sure you have the notes page that was also provided to you on the Google Classroom in front of you. You'll be taking extensive notes as we start the topic of vibrations and waves. Now, this is really an independent study topic for you to hopefully have already gotten started on and to complete, tested on after winter break. But a lot of the vocabulary is important to get out of the way right from the very beginning, and also we'll be doing a lot of demonstrations in class to help you visualize some of the things you just can't get just from doing the reading alone. Now, certainly you also have the reading supplement, which is going to lead you through, guide you through the reading in this textbook, but we want to get some of the stuff out of the way right from the beginning. Now, the topic is really in two parts. There's vibrating objects and waves, and the reason why you put the two together is there's a lot of shared vocabulary between the two. So let's start right from the very beginning with defining what a wave is. So we're on the front page of your notes page called Wave Vocabulary, starting with the definition of a wave, which we define here as a transfer of energy or information without the transfer of matter. As we go through these definitions, feel free to pause the video whenever you need to write down the notes yourself. We also define a wave as a disturbance that propagates through space and time. So you see the difference between a wave and an object. Let's say, for example, I'm in the front of the room giving one of my amazing lectures when I notice a student near the back of the room didn't get enough sleep last night, so his eyelids are starting to droop and I need to get his attention. So I have a couple ways to do so. I could take the marker that I'm using to write on the board and throw it at him and try to pelt him in the head to get his attention. Of course, I don't think that's a very good idea. I'll probably get in some trouble for doing so. But in doing that, some information will transfer from me to him. The information is for him to wake up. In doing so, also matter has transferred from me to him, the matter in this case being the marker. But a wave gets the information there without matter going from here to there, without a transfer of matter. So if instead of throwing a marker, I just yell at the person, "Hey, wake up!" that will get the information from me to him without anything actually traveling from me to that student. In doing so, I've disturbed something in between me and him. I've created a disturbance that propagates through space and time. Propagates is really just a fancy word for travels. So I've disturbed something, and a disturbance travels through space and in time to get to the intended destination. What does it travel through? Well, we call that the medium. That's the matter through which a wave travels. In the example of me yelling at the student, I created a sound wave which travels through the air. The air is the medium that carries the energy. So I vibrate the air molecules right in front of my mouth, and then those molecules hit the next molecules down the line, and the energy gets transferred to pocket, air molecules to air molecules, until the energy gets to the intended receiver, and it vibrates inside their ear, and they receive the information. But again, in doing so, no physical object goes from me to the intended receiver. As the creator of the wave, I am the source, whatever produces the wave or where the energy comes from. I created the wave, the disturbance through the air. I am the source of that wave. The source also has an important job in terms of the wave. The source determines the frequency of the wave. We can categorize waves in different ways. One is numbers 4 and 5 on your page, mechanical versus electromagnetic wave. The definition of mechanical wave is a wave that's created by and transfers mechanical energy. And of course, you know mechanical energy or kinetic and any form of potential energy. A special property of mechanical waves is that they require a medium. There has to be some matter in between the source and the observer to carry the wave energy. Let's suppose number 5, which is an electromagnetic wave, a wave created by nuclear reactions or accelerating electric charges, created in very different ways than mechanical waves. You may recognize the phrases nuclear reactions or accelerating electric charges, and you hopefully associated that with another type of wave, one that particularly can travel through a vacuum, because electromagnetic waves do not require a medium. They can travel through the empty vacuum of space. So you put that all together, a wave that can travel through empty space, created by nuclear reactions or accelerating electric charges, and of course the prime example of an electromagnetic wave is light. Sound is a mechanical wave. It requires a medium. It requires the air between my mouth and the person's ear to carry the wave energy. We can also categorize waves by how the wave vibrates. And the next two terms on your page, transverse versus longitudinal, describe those types. We'll leave those until we're together in class. We can do some demonstrations and there's space there to draw some pictures. Also on that page is the behavior of a wave at a boundary. We'll leave that also for some demonstrations we'll do in class. Let's go right ahead and transfer to the next page on your notes where we're going to take a look at a picture of a wave. So here we're looking at the picture of a wave. Perhaps it's a water wave. It's a transverse wave that the particles of the wave are vibrating up and down, while the wave itself might be traveling to the right. So maybe there's maybe there's a wave produced in water where this line down the middle might be what the water looks like when there's no wave. Maybe you're in a pool and you're eye level with the water and there's no disturbances happening in the pool, and so the water is nice and calm, and then something creates a disturbance and the water bobs up and down, creating this transverse wave. And so our first term here is equilibrium, the appearance of the undisturbed medium. And we can go right ahead and label number 1 in this box, pointing to that horizontal line, what the water would look like without the water wave in it. Next term is amplitude, the largest distance from equilibrium. We give a symbol capital A to that. And the units for amplitude are meters because it is a distance. For all sorts of distances the wave gets from the equilibrium, the largest it gets is what we call the amplitude. And we can go ahead and label that on the picture by those arrows, showing the maximum distance above equilibrium, the maximum distance below equilibrium. Either one of those would be measured as the amplitude. And now we'll take a look at some particular points on the wave. The highest point on the wave is called the crest. It would be the hill in the picture. You should be able to see 2 crests on the picture. We'll label a capital number 3 there. Next term is trough. That's the lowest point in the wave. That would be the valley on the picture. There are 2 troughs on the picture. We'll label number 4 there at the lowest point. So crest and trough are locations on the wave. The amplitude is the measurement from equilibrium, or that line down the middle, to get up to the crest or down to the trough. Our next term, number 5, is cycle, one complete repetition of the pattern. There's all sorts of ways to see the cycle in the picture. Hopefully you should be able to see that there are 2 complete cycles. If you start right here at the beginning at equilibrium, here is half a cycle when it returns to equilibrium. The full cycle is when it completely returns to equilibrium and it's about to do the same thing. So here it's going up, and here it's going up as well. And so from equilibrium to the second, or really I guess the third equilibrium on the picture is a one cycle of the repetition of the pattern, and then we repeat again for a second complete cycle. But really any place where it repeats would be fine. So if here we start a crest, and it goes down through trough and back to crest, this right here is one cycle. Or if we start here at trough and go up through crest and down through trough, this also would be one cycle. So you can put number 5, any of those places. Equilibrium to equilibrium, crest to crest, trough to trough. Really, we can identify any position. So if we were to start here one of these dashed lines up, and it goes down, and it gets that same dashed line, and it's about to repeat exactly what it was doing before, that would also be one cycle. The measurement of this is called the wavelength. This is number 6, the length of one cycle. The symbol we use for wavelength is this Greek letter. That's the Greek letter lambda. If you're having trouble drawing it all fancy like this, you can imagine drawing an uppercase capital X, so 2 diagonal lines, just missing the upper right-hand portion. So again, just 2 diagonal lines, one like so, and one like so, like a capital X missing the upper right-hand part. That would be an easy way to draw the lambda. This is the length of one cycle. And so, of course, anytime we see a cycle on the picture, we can label that as wavelength as well. So you can put a 6 in the box right below each of those cycle boxes. The length of that is one wavelength. The equation for wavelength is, the units for wavelength are given meters because, of course, it is a length. And the way to figure out the wavelength is you take the whole length you see of the wave and divide it by cycles. Now, we mentioned that waves propagate or travel in space and time, so we'll call these space cycles. Really, we're taking the space we see, all of the waves that are there, the whole length, and splitting it up by the number of cycles that appear in that space. In this case, we would measure this whole length, divide by the 2 cycles. This would get the wavelength, the length per cycle. Plus, I like the term space cycle because it conjures up images of motorcycles in space. That sounds pretty cool. Okay, so we'll box it in as a new equation. Our next term on the page here is period, which we define as the time for one cycle. Now, we've seen period before, and we know the symbol is a capital T. Back when we did circular motion, it was the time for one revolution, or one once around the circle. Here's a similar idea. It's the time for one cycle, one repetition of the pattern. So, of course, we know the units are going to be in seconds. We can find the period the same way we did it back when you did the flying pig, the conical pendulum activity. You would take the total amount of time something happens and divide by the number of things that happen. So in this case, it is total time divided by number of time cycles. Again, waves propagate in space and time, so we have to differentiate between space and time cycles. Again, space cycles are ones you can sort of see. When you take a picture of this and freeze it in time, you can see the cycles in space. If you looked at one particular point on the wave and froze it in position, just watch that one point go back and forth and back and forth, the back and forth, that would be a time cycle, the time to return to its same position. Plus, I like the phrase time cycle because now it conjures up an image of a time-traveling motorcycle. Our next term on the page is frequency. Now, it's actually very difficult to define frequency, besides using frequency in its own definition. Like, it's how frequently something occurs, and you can't use a word in its own definition. So we'll go right to the equation. The symbol for frequency is lowercase f. Now we'll go right to the equation. We'll define it as the number of time cycles divided by total time. In other words, how frequently cycles are created, cycles per time. The units for this would be cycles per second, although the cycle itself is really just a counter, so sometimes it's sort of gotten rid of, and it's just 1 over seconds or inverse seconds. And we do give a name to the inverse second. It is called the hertz, and it's capitalized after Mr. Hertz, so it's a capital H, lowercase z. Now, if we take a look at these two equations side by side, the equation for period and the equation for frequency, hopefully, of course, you see a relationship between the two. We should be able to say that frequency is the inverse or reciprocal of period. Really, they're inverses or reciprocals of each other. Just to make sure very clear, this on top here is the number 1. That's not the lowercase l, that is the number 1. It is 1 over period, the inverse or reciprocal of period. Next, we want to talk about the speed of a wave, or how fast a wave goes, and one of the important consequences of this is that the speed of a wave is determined by the medium itself, the matter through which the wave travels. We'll be exploring this in class. We'll do some demonstrations to show this. To figure out the speed of a wave, we go with our original definition of speed, where v bar equals distance over time, average speed equals distance over time. Now, as long as the medium remains the same, we'll assume that the speed remains the same, so we can drop the bar part of it, but we'll replace the distance and time with more wave-like quantities. And so if we imagine a wave traveling, how far does it go in one cycle? It will travel one of its own wavelengths, the length per cycle. How much time would it take to do so? Well, that would be the period, the time per cycle. So we'll replace distance and time with wavelength and period. So v equals lambda over t. Just playing a little bit of algebra tricks here. We can pull a 1 over a period to the outside. And why would I do that? Well, hopefully you see that 1 over a period, of course, is the same thing as frequency, and we'll define speed as frequency times wavelength. In fact, this is the more commonly used equation, v equals f lambda. Nothing wrong with lambda over t, just this one's a little more common. And here I just want to highlight the fact that these two equations are for the speed of a wave only. It should make perfect sense now, but you might find yourself doing some problems and trying to apply either of these equations to actual physical objects. But then hopefully you notice that you're talking about, for example, the frequency, and objects don't have frequencies. That wouldn't make a whole lot of sense. And so it should be pretty clear that these are for the speed of a wave only.